Okay, now we talk more about the minimum spanning tree problem, the Prim's algorithm for the minimum spanning tree problem. So you can see, as I have already said, that the idea of Prim's algorithm is that you maintain a set V minus A and a set A, and the V minus A, the set, the vertices will be in a priority queue keyed with the weight of the least weight edge connecting it to a vertex in A. Okay, so there will be a set A, and initially there will be empty, then you put the one vertex there, the starting vertex, and from that vertex all the edges going out to the set V minus A, you order them in a priority queue, and based on the edge weights connecting the vertices, connecting the edges, connecting the vertices in set A and set V minus A, and then whichever is the minimum, we will choose that and add it to the set A. Let's see with more detail with the algorithm. Okay, so initially this part is the initialization part. Okay, initialization part. So in the initialization, what we do, we set the vertex q. We set all the vertices in the graph, given input graph, to the priority queue q, and then we key the vertices initially with infinity, okay, for all vertices in V. So all vertices initially we consider, suppose this is a given graph, given input graph, initially we say that all the vertices, they are the keys are infinity. Okay, so let's set them to be infinity. So these are the vertices in the graph, these are all set to infinity. This is this step, okay, for all small v belonging to capital V. That means all vertices belonging to the set of vertices. Now take a starting vertex S and make the distance estimate 0. You can take any arbitrary starting vertex. Suppose here, let's say this one, okay, this one we make the starting vertex, make the S, and their distance estimate is 0. Okay, so now we have the starting vertex S whose distance estimate is 0, and all other vertices are having different distance estimate. Now we can even name them, like you can say this is A, this is B, this is C, this is D, this is E, this is F, and this is G. Okay, so these are the we key their weights, age weights, as infinity. Now we can create a priority queue here where we start from S, and from S then A, then B, then C, D, E, F, and G. Okay, so for S this is 0, and for everybody else the key weights are infinity. Okay, so now we take out the starting vertex from that set V minus A and put it in the set A. So we take out this one. Okay, so now when we take it out, we check what are the vertices. You see, while q not equal to phi, so all other vertices, in the queue we put all these vertices. Okay, so this is the vertices in the queue. Okay, so now from the queue is non-null, so from this non-null's priority queue q, you extract mean. I extract the minimum weight estimate. What is the minimum weight estimate here? This is the minimum weight estimate, because this is 0, the S, and all other are infinity. So I take this one out. Okay, so like here we circle it, and then what we do, we say that for each vertex adjacent to you, please remember adjacency is between vertices and incidence is between edges. For each vertex be adjacent to you. What are adjacent to, here U is S, so this is A, this is C, and this is G. So now let's write their distance estimates. So if V belongs to Q, do they belong to Q yet? Still A, C, and G, yes, they belong to Q. If their distance estimate WUV is less than key of V, this is the weight of the edge connecting U and V is less than the key V. So S to A, the edge weight is 15 and the distance estimate of A is infinity. So this condition is satisfied. Weight of edge U and V, that means S to A, is less than the key of A, which is infinity. Then what we do, key of V is replaced with this new distance estimate, which is actually the edge weight connecting S to A. Okay, so this is called decrease key operation. So I reduce the key, I change the key, update the key, you can say, modify the key. So the new key is here, this is 15. So let's change A to 15 here, and G to this edge connecting S to G, which is 10, and this edge S to C, infinity, change to 7. So B is now, sorry, not B, B is infinity, C is 7, D is infinity, E is infinity, F is infinity, G is 10. Okay, so now in the priority queue, there are multiple infinities and there are 3 numeric values. What are the minimum? Now I have done this. I set the pi of V to U. So this their distance estimate have been calculated from this. So we set the parent of U to V. So now it's actually this way. So parent of, make this way, doesn't really matter, this is just for drawing the final tree. Okay, so now again we start from the beginning. Q is not null, so what we do, extract the minimum. So what is the minimum here? Now 7 is the minimum. Okay, so 7 is the minimum means we take it out. Okay, so 7 is not there anymore, so this is now taken out. Okay, so now from 7 we will check that Q not equal to 5, extract the mean 7. For each vertex adjacent to 7, we check if that vertex belongs to Q. So this is adjacent to 7, but it does not belong to Q anymore. S has been taken out before. So what are the still adjacent? B is adjacent, D is adjacent, and E is adjacent. So now you check their distance estimates or the weight estimates and replace it with the edge connecting it with those vertices if the distance or the weight estimates are higher. Like from C now, what are the, it's B, D, and E. So now the distance estimate of B is, instead of infinity, this is 9. You see the edge connecting it is 9. So B is 9. Then C to D is 12, because this distance, this edge weight is 12. That is D is 12, and E is 5. E is 5 because C to E edge is 5. C to E edge is 5 now. Okay, so rest are infinity. So this is 10, this is 15. So one is still infinity. So now among this we choose whichever be the minimum one. Which is minimum one? 5 is minimum one. Okay, so now we just follow the same algorithm. We continue. 5 is minimum one, so we take out 5 and we see all the vertices which are connected to 5 and see which is still in Q. Okay, so like this 5 to this E to D, there is a edge which is 6. The edge weight is 6. So this edge weight is less than the weight of the edge is less than the key. So we can change this key from 12 to 6. Okay, so and there is a edge here E to F, so which is 14. So change this to 14. So here for D, this 12 is changed to 6. For F, this is changed to 14. This is the last infinity, and this is not in the Q, priority queue anymore. And there is one more here, 8. E to G is 8. So this change this 10 to 8. So this 10 is now 8. This 5 is gone, so this 9 and 15 are still there. Okay, so now we got it. Now among this priority queue, we choose the next minimum, which is 6. 6 is this, so we take it out and we check all the vertices which are adjacent to it, and we find that the vertices adjacent to it are not anymore in the priority queue. Okay, so then we check out the next minimum, which is 8 here. So in this 8 we check, which is 8 here. So we highlight it, and from this 8 we see the vertices. This is not in the priority queue anymore. This is not in the priority queue anymore. So okay, where from this came? So set the paths. It came from here, and this came from here. So now there's a path 3 to 14. So this 14 is more than 3. So this 14 will be replaced with 3. Okay, so 14 is now 3, and others are 15 and 9, and these are only this are there. So the next minimum in the priority queue is this 3. So we take it out. All the adjacent vertices are already in the out of the priority queue. So nothing to do here. Let's go and take out the next minimum. So which is 9 here. 9 adjacent vertices are already there, so nothing to do. And then last one remaining is 15. So we take it out also, and there is nothing adjacent to it which is in the priority queue. So the priority queue is now empty, and we got the vertices which are all the vertices, and then we found actually the minimum spanning tree. So this minimum spanning tree is like set this thing. If we take out those edges, we'll find this is 6, this is 5, this is 8, this is 3, this is 7, this is 9, and this is 15. If you add them up, you will find the minimum spanning tree weight, because all the edges we assumed are distinct, if you remember. So there will be a single minimum spanning tree. If the edge weights could repeat, there can be multiple minimum spanning trees with the total minimum weight, a single total minimum weight, but multiple edges add up to make that edge weight. Okay, so make that total edge weight. So here we have shown how the Prim's algorithm works. It's not very difficult. You see there will be a priority queue, and you add all the elements in the priority queue initially and give them key in with infinity key value, and then you take out any arbitrary node and set the key value to be 0 as the starting node, and from that node now you see what are the all other edges going out, and you change their distance estimate from infinity to the edge weights connecting them with the source vertex. Okay, and then among them you choose the minimum one, and again start the or continue the same procedure until the entire priority queue is empty. So this algorithm, the pseudocode, if you see, this part is the initialization part. Initialization part works for all the vertices. You see, initially all the vertices has to be set in the priority queue, then all the vertices has to be set infinity value. So this part is like theta of v times has to be executed, considering v is a large number, and then there will be this part while q not equal to phi. How many times this part will be executed while q not equal to phi? This will be executed v times, because q has all the vertices, you see. So q not equal to phi means every time you take out one, so it's like order of n linear time, or order of mod v times. This will this entire thing will be executed. Now mod v times. So what is the major operation in this mod v times 1? So the major operation is this one. One of them is this, which is extract mean. So we put them in a priority queue. Priority queue is a data structure. You can it's a conceptual data structure, or you can use some other standard data structure like array, using for implementing priority queue, and I'll show you what will be the complexity cost for that. Now another part of the for every vertex you go for all the adjacent edges for each vertex. So what are the adjacent edges for each vertex? What will be the total count for that? We have studied about a handshaking lemma, and we know that for each vertex, the adjacency, if we consider the entire adjacency list, we sum them up, it will be, by handshaking lemma is theta e, theta e times this will execute. It's a degree, degree of the vertex, degree of u. Okay, so degree of u is actually, sum up of the edges, so that is theta e times, so this is theta e, and this is like theta v. And what is the major operation here? Major operation is this one. Okay, this is the important operation. It's called a decrease key operation. I already told you that whatever be the key value earlier, like infinity, we are changing the modifying key value. Here we have shown that the key value was 12, and we had a connecting edge which is 6, so we change 12 to 6. We go for the minimum one at every stage. Okay, so this is the implicit decrease key operation. Implicit decrease key operation. So we can see that this will be executed mod v times we extract the mean. This is the important operation. So we write the total time is v times t extract mean. Okay, v times t extract mean, and e times, because this is theta of e, as you know, the sum of the degrees in a graph is the equivalent to the number of edges, and e is times we do the decrease key operation. Okay, implicit decrease key operation. So the total time is v times extract mean plus e times decrease key. Now if you try to implement it using an array, or you try to implement using a binary heap, different data structure will give you different results. Okay, so if you try to implement it with an array, the extract mean operation will take, you go over the array continuously until you find the minimum element. So you can do using this order of v times. You have to, check the whole array to find the minimum one. And if you try to do decrease key, it's an easy one. When you find the element, you go there and you just change the value. Okay, just override the value. So this is a constant time operation. So this is order of 1. So what will be the total? It will be v times v, extract mean, v times v plus e times 1. Okay, so it's v squared plus e actually. So which is greater? V squared is greater definitely. So order of v squared. This will be. If you try to do it with binary heap, this can be done. This extract mean can be done using a heap data structure. The operations of heap, and this will be a log n time operation. So it's an order of log v, formation of the mean heap again, and then taking out the topmost element, which is order of log v. And if you want to decrease key, you have to re-heapify, so that will be also order of log v times operation. Okay, log v times operation. So this will be this total will be order of v times log v. That's t extract mean v times log v, and e times log v. Okay, so this is order of v times log v plus e times log v. Okay, in graphs usually number of edges are more than the number of vertices. Okay, usually. So so most of the time this can be approximated as a for the higher order term, which is e times log v. Okay, e times log v, because edges are mostly higher in number than the number of vertices. So overall, we have studied the Prim's algorithm. We have shown you the pseudocode and the complexity analysis of the pseudocode, and we have also shown you the execution of an algorithm with an example. And after doing that example, we have shown you the minimum spanning tree, which is this, and this minimum spanning tree will be returned at the end of this algorithm. And we can solve more problems to see how this concept can be made clearer, and what are the other minimum spanning tree algorithms, and we'll discuss them in more detail. Thank you.